Hi, this is John Whitaker for the Probability Graduate Level class, and this is our 15th video lecture. And during this lecture, we want to do an example of Markov's and Chebyshev's inequality, as well as get some background information to enable us to prove the weak law of large number. And that background information is going to have to do with dealing with more than just two random variables at a time. And in addition, we'll also extend at the end types of convergence. We'll look at one specific types of convergence for functions. And the weak law of large number has to do with a specific type of convergence for a sequence of functions. Well, let's go ahead and get started. And we'll get started by recalling these preliminary results for limit theorems in probability. And those preliminary results are, the first one is Markov's inequality. So what it said, it said something like this. It said, let x be a random variable, be a non-negative random variable, and let a be greater than 0. Then the conclusion is that the probability that x is greater than or equal to a is going to be less than the expected value of x over a. So that's what we had proven. And then the second thing is Chebyshev's inequality. And what it says let x be a random variable with finite mean, so expected value, mu, and finite variance, sigma squared. Then, and we're going to let k, be some number greater than 0. Then, the probability that the absolute value of x minus mu is greater than or equal to k will be less than or equal to the variance over k squared. So those are the two things that we had done during video 4. Video 14, I should say, that we're going to now do an example of. So we proved those last time. So as an example, excuse me, suppose the number of specific items produced in a factory in a week is denoted by x, a random variable. X of a week equals the number of items that were produced that week. Suppose it is known that on average there are 500 items produced a week. So here's the first question. It says, what can be said about the probability that the number of items produced in a given week, produced in a specific week, is greater than or equal to 1,000. And for this problem, we're going to use Markov's inequality. And the second part, part D, says the following. It says, if the variance of x is known to be 100, what can be said about the probability that the number of items produced in a specific week is between 400 and 600. So that's our scenario. We got two problems. For this problem, I'm thinking Chebyshev inequality will be the way that we do that. Okay, so for part A, what's being asked of us is we want to know what's the probability that x, the number of items produced, is going to be greater than or equal to 100. Oh, no, sorry, 1,000. We want to be able to say something about that. Now, one thing I want to tell you is that we're going to use Markov's inequality. And what stands out to me about using Markov's inequality, we've got to make sure that the supposition, the hypothesis of Markov's inequality can be satisfied. We've got a random variable here. And in Markov's inequality, the random variable has to be non-negative. Well, x represents the number of items produced, so that has to be non-negative. So that's good. Then we've got some positive number here that's representing a. And so the probability that x is greater than or equal to a by Markov's inequality is going to be less than or equal to the expected value of x over a, which is equal to, here that's going to be 500, which is the expected value of x, over a is 1,000, so we get 1/2. So the probability that x is going to exceed 1,000 is definitely less than a half. It's less than or equal to half. For part B, we're being asked for the probability that 400 is less than x is less than 600. Yeah, that's what we're being asked. And so, one way of viewing that is that's the same thing, to put ourselves in position to use Chebyshev's inequality, that's the probability that x minus 500 so this is kind of centered around 500, 100 units to the left, 100 units to the right, that is going to be less than 100. So the distance between x and 500 is less than 100. Well, that's the same thing. It's not quite Markov's Chebyshev's inequality situation, but the same thing is 1 minus the probability that the absolute value of x minus 500 is going to be greater than or equal to 100. And it's this probability that I can apply Chebyshev's inequality to. Okay, so here, using Chebyshev's inequality, the probability that the absolute value of x minus 500 is greater than or equal to 100, that is going to be less than or equal to, well, it was the variance, which was 100, as given in part B, over this number squared. Well, that's just 1 out of 100. So, the probability that 400 is less than x is less than 600, part B, that's our question, which is really equal to 1 minus the probability that the absolute value of x minus 500 is greater than or equal to 100. Okay. Now, what I'm going to do is to substitute something in bigger for this part. Okay? So here's what I'm thinking. When I substitute something bigger than this probability, then really this I'm subtracting that from 1. Okay? So really this guy right here is going to be greater than or equal to 1 minus 1 over 100. Which equals to 99 out of 100. So what we're saying is the probability that x is between 400 and 600 is greater than 99 out of 100, greater than or equal to. That's pretty strong likelihood. Okay, I'd like to talk about some information where we're relating more than 2 random variables together. And so we're just going to extend a definition we had earlier. So given discrete random variables, x1, x2, up to xn, the joint probability mass function of x1, x2, up to xn is a function f of x1, comma, x2, comma, x3, comma, all the way up to xn, defined by, okay, just as we would before, f of x1, comma, x2, comma, x3, all the way up to xn, what that's equal to is the probability that x1 is equal to little x1, and x2 is equal to little x2, and x3 is equal to x3, all the way up to, and xn is equal to little xn. So that's the joint PMF of x1, x2, all the way up to xn. Well, if we can talk about the joint PMF for more than 2 random variables, well, we'll be able to talk about the joint PDF for more than 2 random variables, and that's what we're going to do next. Here's a definition. All right, so we say the random variables x1, x2, x3, all the way up to xn are said to be jointly continuous. Okay. Jointly continuous. If there exists a function f of x of 1, x of 2, all the way up to x sub n, such that for any a1, a2, all the way up to an that are subsets of R, then the probability that x1 is an element of A1 and x2 is an element of A2, all the way up to x sub n being an element of A sub n, what that's equal to, or given by, is the integral. We're going to have the n integral, so here I'm going to write down A sub n, integral of A sub n minus 1. We will keep going all the way up to A sub 2, integral over A sub 1, of f of x sub 1, x sub 2, all the way up to x sub n, and then we would have dx sub 1, dx sub 2, dx sub 3, dx sub n. So that's what it takes to be jointly continuous. And in this case, this f of x sub 1, x sub 2, all the way up to x sub n is called the joint PDF of x sub 1, x sub 2, all the way up to x sub n. That's that definition. So again, that's just an extension of the joint PDF between two random variables. Now we did it to n random variables. Okay. Well, another definition that's going to be important to our first limit theorem, the weak law of large numbers, is the following. It says let x sub 1, x sub 2, all the way up to x sub n be random variables. The collection of random variables x1, x2, all the way up to xn are said to be independent if for all a sub 1, a sub 2, all the way up to a sub n that are subsets of R, the probability that x sub 1 is an element of A1 and x sub 2 is an element of A2 and x sub n is an element of AN, what that's going to be equal to is the product of these probabilities. Probability x of 1 is in A1 times the probability of x of 2 is element of A2 times, and we keep going with this multiplication till we get down to multiplying by x of n being the element of AN. That's what we mean for more than two random variables to be independent. Another definition that's important for weak law of large numbers and other limit theorems is that the random variables x1 and x2 are said to be identically distributed if so their distribution are the same, meaning their PMFs or PDFs are the same. So what I'll say is if f sub x sub 1 of t is the same thing as f sub x of 2 of t. Let's look at an example of that. So as an example, let's say a coin is tossed. Let x of 1 of heads be equal to, let's say, 1, and x of 2 of tails be equal to 2. Let's also assume, or also know that an urn contains 3 red balls and 3 white balls. A ball is selected at random. Okay. We're going to let another random variable, x of 2 of red ball, be equal to 1, and x of 2 of W be equal to 2. Okay. Note, f sub x of 1, well, this is going to be the PMF of x of 1, and so the output values are 1, and the chance that you got 1, that's what this represents, is 1/2. And f sub x of 2, well, that's the chance that, I'm sorry, should be x of 1. That's the chance that the random variable x of 1 was equal to 2. Well, that happens when we got tails, and that happens half of the time we have a parallel. Also, the PMF of x of 2, well, its output values are, and for this probability mass function, it's the input values, so the output values of x of 2. They're either 1 or 2. And the chance that x of 2 was equal to 1, well, that's the chance that you got, let's see, a red ball, and there were 3 red balls out of 6 balls, so that's 3 out of 6, well, that's 1/2. And f sub x of 2 of 2, that's also equal to 1/2. So what we can say is x of 1 and x of 2, since they have the same PMFs, they are identically distributed. All right, having said that, we're ready to look at the weak law of large numbers and give proof. So here's what it says. It's the weak law of large numbers. Okay. This proof is going to be based on Chebyshev's inequality. So here's the statement. It says, let x of 1, x of 2, x of n, all the way up to x of n and beyond, be a sequence of independent and identically distributed. A lot of times we abbreviate that with IID, independent, identically distributed. Random variables. Each having finite mean mu. Okay? Well, I'll write it down like this. Finite mean, that means the expected value of x of whatever. So the expected value of any one of these is equal to the same thing, it's just mu. Because they're identically distributed, that's what will happen. Then, for any epsilon greater than 0, the probability that the absolute value of x of 1 plus x of 2 plus all the way up x of n over n minus mu will be greater than or equal to epsilon. That probability goes towards 0 as n goes towards infinity. So we're talking about some kind of convergence here for this sequence of random variables. And if you look at adding up the x of 1 up to x of n, well, we're thinking of these things being independent, identically distributed. And we divide by the number of random variables involved. So we're looking at these output values, and we're dividing by the number of output values we have. That ought to be, because they're identically distributed, that ought to be like their average. And so we're saying that the distance that this is from the average is the probability that that is greater than or equal to any fixed number epsilon. The more random variables you have involved, the probability that that's bigger than any epsilon goes to 0. Meaning that this average, or the sum of the random variables over n, that's how we calculate average, this distance from away from the average is going towards 0 in probability. And I said in probability, that's a type of convergence that we can have. And we'll talk about that later. It turns out it's called a weak log large number because the type of convergence is in probability, which is not that great of a type of convergence. Well, we want to prove this. And I'm going to present a proof that has one more additional assumption. So the statement is true, but in order for us to make the proof manageable, we're going to have one more condition. And as I said earlier, the proof's going to be based on Chebyshev's inequality. Okay. So here's the proof. We're going to let x of 1, x of 2, all the way up to x of n and beyond be a sequence of independent and identically distributed random variables each having finite mean mu. Okay? So I'll write that down. Expected value of x of I is equal to mu. So, for the purposes of this proof, we will also assume each random variable has finite variance. So I'll say the variance of x of I, we'll call it sigma squared. Okay, what do we want to show? We want to show that the probability that the absolute value of x of 1 plus x of 2 plus all the way up to adding up x of n divided by n minus mu, that's greater than or equal to epsilon, that goes to 0 as n goes towards infinity, and that's for all epsilon. Okay, so I'm going to let epsilon be given and show it's true for that particular epsilon. And I say for all epsilon, it's for all epsilon greater than 0. Okay, I said I was going to use Chebyshev's inequality. And so what we're going to do is have to show, well, let me back up. To use Chebyshev's inequality, what we're going to have to do is we're going to say that this is our random variable, like x in Chebyshev's inequality. And what we've got to show is the expected value of x is mu. Okay, and then we've got to show that it has finite variance to this random variable to apply to Chebyshev's inequality. So that's what I'm going to work on. Okay. Well, note the expected value of x of 1 plus x of 2 plus x of n over n. Well, that's equal to, well, I can pull out the n, 1 over n, and it's the expected value of x of 1 plus x of 2 plus x of n. What we've shown is the expected value of two random variables being added together is the expected value of each of them. And by induction, you can extend this and say this is the same thing as 1 over n times the expected value of x of 1 plus the expected value of x of 2 plus forever up to the expected value of x of n. Now, each one of these expected values are the same because of the identically distributed nature of the sequence of random variables. And so they're all mu. So this is mu, and so how many mu's do we have? We have n of them, n times mu, which is just mu. That's what we want. All right. Also, talking about the variance of x of 1 plus x of 2 plus all the way up to x of n over n, well, what's that going to be equal to? By our formula, it's the expected value of x of 1 plus x of 2 plus x of 3 plus, keep going, all the way up to x of n over n to be squared minus the expected value of x of 1 plus x of 2 plus x of n over n, that result to be squared. Well, we already got that. That's going to be mu squared. So this is what we got to concentrate on. Okay, well, the expected value of this x of 1 plus x of 2 plus x of 3 plus x of n, all the way up to that, over n to be squared, that's equal to, well, is the expected value of x of 1 plus x of 2 plus x of n times x of 1 plus x of 2 plus x of n all over n squared. I can pull out the 1 over n squared, and I will, and have just the expected value of this x of 1 plus x of 2 plus all of x of n times itself, so x of 1 plus x of 2 plus itself. And I'm going to do this multiplication. So we get 1 over n squared. When I multiply this out, this is the expected value of the first one is x of 1 times x of 1. Second one that I have is x of 1, so I'm taking x of 1 times all these guys. X of 1 times x of 2. Plus I keep x of 1 times x of 3. Plus we keep going all the way up to x of 1 times x of n. I'm done with x of 1 here. Now I'm going to have plus x of 2 times x of 1. And I'm going to keep going. I'm going to have x of 2 times x of 2. I'm going to keep going. And eventually I end up with x of 2 times x of n. And I keep going. And the last thing I get is x of 1, x of n times x of 1. I keep going for x of n. And I end up with x of n times x of n. All right. Now, the expected value of the sum is the sum of the expected values. And so, I'm going to rewrite this as 1 over n squared times the expected value of x of 1 times x of 1 plus the expected value of x of 1 times x of 2 plus, we keep going, and we end up with the expected value of x of 1 times x of n, that's all the x of 1, plus, now I have the expected value of x sub 2 times x of 1, the expected value of x of 2 times x of 2, plus, and we keep going, so I get the expected value of x of 2 times x of n, and then we keep going for each one of the first random variables in that first collection in the same method, until we get to the x of n in the first grouping, and that will be times x of 1, expected value of that. Plus we keep going to get to the expected value of x of n times x of n. Now, some of these expected values are the expected value of one thing with itself. So I'm going to look at those. And I'm going to say that's 1 over n squared times, well, how many of those do I have? Well, it will be the sum, I don't know how many I would have, but it would be the expected value of x sub I squared, if you will, because this is the expected value of x sub 1 squared, as I ran from 1, well, to n. I'd have n of them. Plus some other sum where you're just having 2 of them together. So expected value of x of 1, or I should say x of I and x of j. I'm not going to say how many there are yet, but that's what we have. Okay, this is equal to 1 over n squared. Here's the sum. I'm not going to touch it. Yeah, I am going to touch it. So, because we have the random variables being identically distributed, that the expected value of x sub 1 squared is the same thing as the expected value of x sub 2 squared. It's the expected value of any of the random variables being squared. So I'm going to say this is the same thing as x sub 1 being squared. Plus, here, this is a sum of expected value of the product.
Now we know each one of these random variables are independent from each other. And so the expected value for two independent random variables is nothing more than the expected value of the first guy times the expected value of the second guy. Here, of course, I and j are different. So this is equal to 1 over n squared. This sum, well, let's see. This is the same thing. It doesn't depend on pi. So I'll leave it as is. And I'm summing it up n times. So it's n times the expected value of x sub 1 to b squared. Here, how many of these terms do we have? Well, let's see. How do we get one of these terms? They come from having an x sub I and x sub j and they're being different. So how do I get them? What I'm doing is from that first group, I'm picking one, and I'm picking a different one from the second group. So really, they're n random variables, and you're picking two of them. So here I have n choose 2. So expected value of x sub I, x sub j. That's not quite right, it's close. Okay. The reason it's not quite right is that this n choose 2 is like having, it's the number of ways of having two of them drawn from the x sub 1 to x sub n of them. But once we choose two of them in our listing up here, so let's say x sub 1 and x sub 2, okay, that's one of these n choose 2 ones. But we don't have just one of those. We have two of them because here's x sub 2, x sub 1 again. And so really there's double the n choose 2 number of ways. So that's what we are. Okay, so that's equal to 1 over n squared times n times expected value of x sub 1 to b squared. And here we have plus 2, and then n choose 2 is n times n minus 1. All over, well, it's n factorial over n minus 2 factorial. That's the n times n minus 1. That's what produces. And then it's 2 times 1. And then the expected value of x sub I times the expected value of x sub j. Well, they're identically distributed. Each one, the expected value of the x sub whatever is always mu. So we get mu times mu, or just mu squared. So this ends up being 1 over n squared, I'll distribute this, times n times the expected value of x sub 1 squared, plus the 2's cancel each other out. So I'm left with n times n minus 1, that's n squared minus n over n times mu squared. We'll simplify that. This is 1 over n, the expected value of x sub 1 squared. This would be plus, oops, this should be n squared. So here it's mu squared minus, this will be 1 over n mu squared. And that's what I have. So the variance of x sub 1 plus x sub 2 plus x sub n all over n, well, that's the expected value of this quantity to be squared, which we just found. It's 1 over n squared times the expected value of x sub 1 to be squared, plus mu squared. It's not 1 over n squared, it's 1 over n. Plus mu squared minus 1 over n times mu squared. And then we should subtract from that the expected value of this quantity and that whole thing squared. But we just showed the expected value of this quantity earlier in the proof was equal to mu, so we square it, we get mu squared minus mu squared. So this plus mu squared and this minus mu squared cancels. So what I'm left with is 1 over n times the expected value of x sub 1 squared minus 1 over n times mu squared. Remember that. Well, mu is nothing more than the expected value of x sub 1. And I can factor out 1 over n in all those true terms. when I do, we get that this is equal to 1 over n times the expected value of x sub 1 to b squared. And then minus, again, I've taken out the 1 over n, it said mu squared, but that's just the expected value of x sub 1 to b squared. But what's in the bracketed expression, so 1 over n is outside of it, what's in the bracketed expression is the variance of x sub 1, but that's 1 over n, the variance of x sub 1, we've got a symbol to denote it, is sigma squared. That's what I got. Okay. So, the probability that x sub 1 plus x sub 2 plus, we'll keep going, plus x sub n over n, inside absolute values, minus mu, is greater than or equal to this fixed epsilon, is less than or equal to, and I'm using Chebyshev's inequality, it's less than or equal to its variance of this, which we just found, is 1 over n sigma squared, over this guy squared, so epsilon squared by Chebyshev's inequality. Wonderful. Excuse me. So, what I'll say is that 0, because it's a probability, this guy's got to be greater than 0. 0 is less than or equal to the probability of this, x, that's the value of x of 1 plus x of 2 plus x of n, over n, minus mu, being greater than or equal to epsilon, which is less than or equal to, rewrite this is sigma squared over n times epsilon squared. Now, since, remember what we're trying to do is show that the limit of this is n goes to infinity, there's a 0. So since the limit as n goes to infinity of 0, this guy, is equal to 0, and the limit as n goes to infinity of sigma squared, as we're thinking of as a fixed number, times n times epsilon squared is a fixed number, this is equal to 0. Then by the squeeze theorem, for sequences. Okay? So this guy's n gets big goes to 0, this guy's n gets big goes to 0, it's going to force the middle guy to go to 0, so that's what I'm going to write. Then the limit as n goes to infinity of the probability of x1 plus x2 plus xn over n minus mu being greater than or equal to epsilon. That equals to 0. And that's what we were trying to prove. So we proved the weak law of large numbers under the conditional assumption that the variance for each one of the random variables involved was finite, sigma squared. And again, the statement is true without that, but the proof is much more difficult, so we just do it with this extra assumption. Okay. I said that this type of convergence for the sequence of random variables is called convergence in probability. What I want to do is spend a little time so we get some understanding about these different types of convergence for sequences of functions, and we can think of these random variables as functions. Okay? So here's a definition. We say let f sub n be a sequence of functions each with the same domain, each with domain A, I'm going to say a subset of R. Didn't have to be a subset of R. Then we suppose for each x in A, the sequence f sub n of x converges. So this is a sequence of numbers, and we're saying it goes to something. Then we define a function I'll call it big F of x to be equal to the limit as n goes to infinity of the f sub n of x. So that's how we define this big F. Then we say the sequence f sub n, sequence of functions, I don't like the way I put it. Then we say the sequence of functions, f sub n converges pointwise to f on A, and that's what we're defining, pointwise convergence, okay? All right, let's look at an example. And that's what we'll conclude with. So here we'll let f sub n of x be defined by x to the n, and we're only going to define it on the closed interval from 0 to 1. Then f sub n of x converges pointwise to this big F, which is going to be defined by, it's 0 if x is an element of 0 to 1, but it's 1 if x is an element, or if x is equal to 1. I'm going to look at this pictorially and then we'll call it quits. Okay. So, pictorially, I'm just looking at 0 to 1. And if you think about f sub 1 of x, f sub 1 of x is x to the 1. So f sub n of x is x to the n. So f sub 1 of x, the first sequence of the function, it's just it's just x. Well, that's this function. It's a straight line. The next function in the sequence f sub 2 is x squared, x raised to the second. Well, I know it's a cup, and we're looking at this part of it, so it looks like this. And it also has 1, 1 on this graph. X cubed, it looks like this, and this is the part we're looking at. And if you graph it, it kind of swings below this other guy. And that's the way all of these functions do. They keep having this type of pattern. Okay? And so what we're saying here is that for any x value in between 0 and 1, including 0 but not 1, if we look at the output values in our sequence, you can see that they keep going down, the output values, the y values, they keep going down towards 0. But when x is equal to 1, all the function values are 1. And so the sequence of 1, 1, 1, 1, 1, 1 converges to 1. And that's why we have the sequence of little f sub n of x converging to that big F that I've written on that side. And they converge pointwise because they converge for each x value, okay, to that particular
evaluation of big F.
All right, thank you very much. That's enough for this video lecture.